In the previous screencast, I showed you how we can put together a 2-squared factorial design and how we can compute the contrasts and the effects. In this screencast, I'm going to show you how we can statistically analyze those effects to see if they are significant. We're going to continue with this example with our ultrafiltration membrane. We have 2 factors and 2 levels, so this is a 2-squared design. We want to explore if additive in time independently have effects on separation, and we also want to explore if there's an interaction effect due to additive in time. There are 3 ways to statistically prove that a factor has a significant effect on the response, and they are all mathematically equivalent. You've already seen one of these techniques. We can create a regression model. Are the parameters significant? For example, we can create a multilinear model down here where we have simple x1 and x2 terms. x1 corresponds to additive, x2 corresponds to time. x1, x2 is the interaction between those two. The second technique is to use ANOVA. We can partition the sum of squares. Is the variance attributed to the factor significant? So that brings up the third one, effects analysis. Are the effects that we determined in the previous screencast significantly greater than an error of the effect? So number 3 here is what we'll be doing in this screencast. So we've calculated our contrasts and our effects for this 2-squared factorial design. We need to determine if the effects are significant. Whenever we're determining if something is significant or not, we're comparing it to an estimate of the uncertainty. For example, we might have something like this, where this might represent the distribution of effects. Effects are going to be randomly distributed. You can have some that are negative, some that are positive, but mostly they're going to center around 0 if the effects are insignificant. But if we get way out in the tail with one of our effects, either an upper tail or a lower tail, then we can conclude that that effect is significant. And so in order to do this analysis, just like everything else we've been doing in this course, we have to somehow come up with an estimate for the standard error. And so that's what we need to determine before we can do a statistical analysis. We can determine the variance of an effect by this equation. This is just the standard error squared divided by n divided by 2 to the k minus 2. K is the number of factors that we have, n is the number of replicates that we have done. The standard error squared we can estimate by the pooled variance of individual responses. In other words, we can compute the variance for each treatment level, and then we can kind of average those and put those together as a pooled estimate. And I'll show you how we can do that here in Excel in a few minutes. We can also calculate that similar to how we've calculated standard error squared previously. We can take SSE, in this case dividing by the degrees of freedom, and we can divide that by 2 to the k times n minus 1. If we've got equal number of replicates for each sample group, it's much easier to just calculate a pooled variance. The standard error of the effect, therefore, we can take the square root of the variance, and we get this equation. Once we have estimates for the standard error, we can set up a hypothesis test. The null hypothesis, the effect is equal to 0. The alternate hypothesis, the effect is not equal to 0. So we're going to perform two-tailed tests here. We typically perform two-tailed tests just because automated tools, they don't really know if effects are positive or negative until they actually compute it. So a lot of times we just do two-tailed tests. The test statistic is the effect divided by the standard error of the effect. And then we compare this test statistic to the t distribution with 2 to the k times n minus 1 degrees of freedom. In our case, in our example, this is going to be 12. And if that test statistic, if the absolute value is greater than our critical value based on 2 to the k times n minus 1 degrees of freedom, then we accept the alternate hypothesis. Otherwise, we reject the alternate and fail to reject the null hypothesis. So I've got a starter file here, ultramembrane statistical starter. You can work through this if you'd like. We have our contrasts and effects that we calculated in the previous screencast. I've got my number of replicates here. This is named n. We've got k. This is the number of factors, and that's 2. I also over here have a y dot dot bar, and that's simply the average of all of our replicates because we're going to need that here in a little bit. Let's go ahead and first calculate the variance of each of our treatments. This is simply the variance var.s of our 4 replicates for when A and B are both at their low levels. I can easily copy this down, and those are the variances for each of the groupings of 4 replicates. The pooled variance, therefore, is just the average of those 4, and you can only do this if the number of replicates for those 4 different treatment groups are the same, which they are. And then we can simply take the square root of that pooled variance to calculate our standard error. I've already named this cell SE for standard error. Now I can use this equation over here to calculate our test statistics, the effect over the standard error of the effect. We actually need to calculate the standard error of the effect first, which is given by this equation down here, and that's the square root of our standard error squared divided by n divided by 2 to the k minus 2. And when we do that, we get a standard error of the effect of 1.15. Now I can calculate my test statistic. I've named this cell SE underscore effect for standard error of the effect. And now let's go up here, calculate our test statistics. That's just the effect that's in the cell above, divided by standard error of the effect. And we get a test statistic for the effect of A of 13.6. We can copy this over, and you see that all of those test statistics are pretty large. But let's calculate a p-value to determine how rare it is to get those t-values, those test statistics. The p-value here we're going to base on the t-distribution, two-tailed. I can use my test statistic there as the first argument, and then we're going to compare to the t-distribution with 2 to the k times n minus 1 degrees of freedom, and we get a p-value for A of 1.16 times 10 to the negative 8th. So that's definitely significant. We can drag this over, and we see that the effect of B is also quite significant. Whenever you have a negative test statistic, we have to go in here and we have to do the absolute value of that test statistic. I could have done that for all of these, probably better practice. And that's what we get for the p-values. So this is showing that the effect of additive is significant, the effect of time is significant, and the interaction effect between time and additive is also significant. We can also convert this to a regression model of our coded regressor variables. So here's our linear regression model. Again, x1, x2 are coded. We can calculate the coefficients in our coded linear regression model by these two equations. The intercept is just the grand average, that's y dot dot bar, and the coefficient of any effect is just the effect divided by 2. It turns out the grand average is 84. We calculated that earlier on the spreadsheet, so that's the intercept of our coded model. We can determine beta 1 by taking our A effect and dividing by 2, so that's 7.83, and we can do the same thing for our B effect, that'd be beta 2, and our AB effect, and that'd be beta 1, 2. And we get these for our coefficients in the coded linear regression model. So the way we got those, beta naught is just equal to the grand average, which I've named AVE. Beta 1 is simply the effect of A divided by 2. Beta 2 is simply the effect of B divided by 2. And then beta 1, 2, that's the coefficient to the interaction term, which is equal to our interaction effect divided by 2. And so that's how we can get the coefficients of the coded model. And going back to our ANOVA results that we did the other day, we did kind of the same thing where we looked at A, B, and the interaction, and we calculated p-values to determine if those sources of variability were significant or not. And if you look at the p-values, they're exactly the same as that which we get using the effects analysis. In summary, you can use all 3 of these techniques. You can use a regression model, you can use ANOVA, or you can use effects analysis to determine if the effects in a fixed effects model are significant.